We tap away on our smartphones, open browsers, manage files, all without really thinking about it. But have you ever stopped and wondered what's actually like going on under the hood?
It's quite something when you pause to consider it.
Right.
An incredibly complex dance is happening constantly, hardware and software working together, mostly perfectly, to make all that stuff possible.
Absolutely. And today we're taking a deep dive into that fascinating, often invisible world of operating systems. It really is the unsung hero, isn't it? The digital conductor making everything happen.
That's a great way to put it. And our goal today really is to bridge that gap between let's say, the big theories you find in textbooks, which can feel a bit abstract sometimes,
Right.
and the nitty-gritty, sometimes surprising realities of how these things are actually built and how they work day to day.
Exactly. We've got insights from a classic textbook, Operating System Concepts by Silberschatz, and also from a very hands-on guide for building a simple OS called Pintos. So hopefully we can uncover some real aha moments that might change how you look at your phone or your laptop. Okay, so let's start right at the basics. What is an operating system, really? I mean, beyond the windows and icons we see.
Fundamentally, it's a program, but it's a special kind of program. Its job is to manage all a computer's hardware, the processor, memory devices,
All the physical stuff.
all the physical stuff, and it provides the foundation for applications to run, acting as that crucial go-between between you and the machine itself.
And it's amazing how different they can be depending on the job, right? Like a mainframe OS is all about squeezing every last drop of performance out of massive hardware.
Right, maximizing utilization, whereas a PCOS needs to handle everything from games to spreadsheets.
And your phone's OS is optimized for touch screens and, well, being convenient.
Exactly. Different priorities, different designs, but the core function remains.
And underpinning all of that is the hardware foundation. You basically got four main parts to any system, yeah.
That's right. You have the hardware CPU, memory, I/O devices, then the operating system itself, then the applications you run, and finally, the user, you.
I found this bit fascinating, the Bootstrap program. It's not even the OS that starts first, is it?
No, not quite. That's a really key point. When you hit that power button, the very first thing that runs is this tiny bit of code stored in firmware like ROM or EEPROM
Firmware.
called the Bootstrap program. Its only job is to wake everything up, initialize the system basics, and then, crucially, load the actual operating system kernel into memory and start it running. It's like the system's ignition key.
Okay, so that gets us into memory. And memory isn't just like one big pool, is it? It's more like a hierarchy.
Oh, absolutely. It's a whole spectrum. You start with the super fast, tiny registers right inside the CPU, then slightly larger, slightly slower cache memory.
Which is still way faster than RAM.
Exactly. Then you get to main memory, or RAM, which is where most active programs and data live. After that, you've got your non-volatile storage.
Stuff that stays when the power's off.
Right, like solid-state drives or SSDs, which are much faster now, and then traditional magnetic hard disks. And you can even go further down to things like optical disks or magnetic tapes for archiving, though that's less common for everyday use.
And the key difference, apart from speed and size, is volatility.
Yes. Registers, cache, RAM, they're volatile.
Yeah.
Power goes off, data disappears. SSDs, magnetic disks, they're non-volatile. They hold onto data. The OS has to manage this whole hierarchy constantly, trying to keep frequently used stuff in the faster layers. It's a trade-off, always, between speed and cost.
And Pintos, our educational OS example, it runs on that standard 80 by 86 architecture, doesn't it?
Yeah.
So even though it's simplified, it's wrestling with these same fundamental hardware ideas.
Precisely. It grounds the theory. You're building on these real hardware concepts, even if it's a scaled-down version.
Okay, hardware foundation set. Now, how does the OS actually make things happen? Let's get into processes and threads, the multitasking magic. First off, what's the difference between a program and a process? Because they sound similar.
They do, but the distinction is vital. Think of a program as passive instructions, like a recipe written down on a piece of paper. It just sits there on the disk.
Okay.
A process is that recipe being actively cooked. It's the program loaded into memory, actually executing with its own state, like which instruction it's on, what memory it's using, what resources it holds. It's dynamic.
Got it. So when I open my web browser, that's a program becoming a process.
Yes, and often Modern browsers will actually start multiple processes, maybe one for the main browser window, one for each tab, maybe even separate ones for extensions.
Ah, so that's why sometimes one crash tab doesn't take down the whole browser.
Exactly. That's one reason. Each process gets its own slice of CPU time, giving you that feeling that everything's running smoothly at the same time.
Which brings us to concurrency. How does the OS manage that illusion, especially on systems that maybe only had one CPU core back in the day?
Right. Well, that's where multiprogramming and time sharing come in. Multiprogramming just means keeping several jobs loaded in memory at once. So if one job has to wait for something slow, like reading from a disk,
The CPU doesn't just sit idle.
precisely, the OS can switch the CPU to another job that is ready to run. Time sharing, or multitasking, takes that further by switching the CPU between jobs very, very rapidly, fractions of a second.
So fast we don't notice the switching.
Pretty much. It creates the illusion of simultaneous execution, absolutely essential for interactive systems, because compared to a CPU, human reaction times are incredibly slow. The computer can do millions of things while you're deciding what to type next.
And now we have multiprocessor systems, SMP, symmetric multiprocessing. That changes things, right?
It does. Now you have multiple CPUs, or multiple cores within a single CPU, all working together. They share the same physical memory and can all run OS tasks or user applications.
So, more power, double the cores, double the speed.
Not quite, unfortunately. There's always some overhead involved in coordinating the cores, managing shared data, avoiding conflicts. So N processors won't give you exactly N times the performance, but it's still a significant boost in throughput. Windows, macOS, Linux, they're all designed for SMP.
And within those processes, you can have threads. What are they?
Threads are like lighter weight processes within a process. A single process can have multiple threads, each executing a different part of the program's code, potentially simultaneously on different cores.
Ah, so that's how one program can really use multiple cores.
That's a major way. Think of a word processor. One thread might handle typing input, another background spell checking, another auto-saving. Threads allow for finer-grained parallelism within a single application.
The programming for that sounds tricky.
It introduces challenges, definitely. Figuring out which parts of a program can run in parallel, and then managing shared data so threads don't trip over each other, that requires careful design. Synchronization is key.
Let's bring Pintos back in. It has some really interesting practical takes on this, like the context switch, saving one thread's state and loading another's.
Oh yeah, the part handles by raw 80 by 86 assembly code.
Exactly. And the manual basically says, don't worry your pretty little head about this part. What does that tell you?
It tells you that some parts of an OS are just incredibly low-level, hardware-specific, and frankly, complex. They abstract it away because for learning higher-level concepts, you don't need to wrestle with the assembly instructions for saving CPU registers. It highlights the layers of abstraction.
Pintos also warns against busy waiting. That sounds familiar from the textbook concept of spin locks.
It's the same idea. Busy waiting is when a thread just sits in a tight loop, constantly checking if a condition is true.
Just spinning its wheels.
Exactly. It consumes CPU cycles doing absolutely nothing useful. It's generally very inefficient, especially on a single core system, because that spinning thread prevents any other useful work from getting done. Spin locks have their place, but you have to be very careful.
And that warning in Pintos about group projects, merging code at the last minute and finding it, doesn't even compile.
Yes. That sounds painfully familiar to anyone who's worked on a software team, doesn't it? It's a universal lesson. Integration needs planning, not just a last-minute scramble. It's a real-world software engineering headache captured perfectly.
Pintos also has these limitations, like user programs initially can't use malloc or floating point numbers. Why?
It's about staged complexity. Implementing dynamic memory allocation, malloc, requires a proper memory manager in the kernel, which isn't built until later, and floating point math.
Yeah, calculations with decimals.
Right. The basic Pintos kernel doesn't bother saving and restoring the CPU's floating point unit state during a thread switch. It's extra work, extra complexity saved for later. It shows how kernel features directly enable or disable application capabilities.
Okay, so the OS is juggling all these processes and threads. How does it keep them from crashing into each other or messing with the OS itself? That's where protection comes in, right? Dual mode operation.
Precisely. This is fundamental. The hardware provides at least two modes. User mode, where applications run, and kernel mode, or privilege mode, where the OS runs. There's a special mode bit in the CPU that tracks which mode is active.
So applications are sort of fenced off.
Exactly. In user mode, certain instructions are forbidden, direct hardware access is limited, and memory access is restricted. If an application needs the OS to do something privileged, like read a file,
I have to ask nicely.
it makes a system call. This is a controlled entry point into the kernel. It triggers a switch from user mode to kernel mode. The OS performs the requested service, if allowed, and then it switches back to user mode before returning control to the application. It's a secure gatekeeper mechanism.
Okay, and managing memory is another huge OS job. Virtual memory sounds like some kind of magic trick.
It kind of is. It's one of the most ingenious OS concepts. The basic idea is to give each process the illusion that it has its own vast private memory space, the virtual address space much larger than the physical RAM actually available.
How does it do that?
It separates the logical addresses used by the program from the physical addresses in RAM. The OS, with hardware help, maintains mapping tables, page tables, that translate virtual addresses to physical ones on the fly.
And this enables things like demand paging.
Yes, demand paging is key. Instead of loading an entire program into RAM when it starts, the OS only loads the necessary pages, small chunks of memory, as they are actually needed.
What happens if the program tries to access a page that isn't in RAM?
That triggers a page fault. It's an exception, but not necessarily an error. The OS catches the fault, finds the needed page on the backing store, usually disk, loads it into an available frame in RAM, updates the page table, and then restarts the instruction that caused the fault.
Wow. So it happens behind the scenes.
Totally transparent to the program, ideally. It just pauses for a moment while the OS fetches the data.
But this can go wrong. I think you mentioned thrashing earlier.
Ah, yes. Thrashing. That's the dark side of demand paging. It happens when a system is trying to run too many processes, or processes that need more memory than physically available. The system spends almost all its time just swapping pages in and out from the disk.
So like page fault, swap in. Oh, wait, need that other page, swap that one out, swap this one in, page fault again.
Exactly. Constant swapping. Very little actual computation gets done because the CPU is always waiting for the disk. CPU utilization plummets and the system grinds to a halt. It's a nightmare scenario.
And even the size of those pages matters. Big versus small.
Yeah, it's a trade-off. Smaller pages mean less wasted memory if a program only needs part of a page, better locality. But smaller pages also mean larger page tables to manage them.
Right, more overhead.
And potentially more page faults. Larger pages reduce table size and I/O time per page, but might waste more memory if programs don't use the whole page. There's no single perfect size.
And Pintos has this amazing moment where suddenly a page fault isn't a bug anymore.
Yes, that's the virtual memory project. Before that, a page fault in Pintos means your kernel code messed up, but once you implement demand paging, a page fault becomes normal. It just means, oops, that page isn't in RAM, let me go get it from the file or swap space. It's a huge conceptual shift.
And implementing it is complex, I imagine.
Very. You need a sophisticated page fault handler. You need synchronization because multiple page faults might happen concurrently on different cores. You need to manage memory mapped files correctly. It shows how a simple textbook concept like paging explodes into practical complexity.
Okay, shifting gears slightly. Beyond active memory, we need long-term storage. Disks, SSDs. How have SSDs changed things for the OS?
Dramatically. Because SSDs have no moving mechanical parts, no spinning platters, no moving read-write heads, the complex disk scheduling algorithms needed for magnetic disks, like trying to minimize head movement, become much less important.
So simpler is better.
Often, yes. A simple first-come, first-served FCFS scheduling policy works quite well for SSDs. It simplifies the OS's storage management task considerably.
And for reliability, there's RAID.
Right. Redundant array of inexpensive disks. Different levels offer different trade-offs between performance and redundancy. RAID 1 mirroring duplicates data onto 2 disks. RAID 5 strikes data across multiple disks, but also includes parity information, so if one disk fails, the data can be reconstructed. It protects against disk failure.
The OS also uses disk for swap space, right? What's that for?
Swap space is used for anonymous memory pages of memory that aren't directly backed by a file on disk, like a process's stack or heap data. If the OS needs to free up physical RAM, it can swap out these anonymous pages to the swap space on disk. It's usually divided into page size slots for efficiency.
And managing all the data on these disks requires a file system. What does the OS provide there?
Beyond just reading and writing data, the OS provides system calls to create files, delete them, reposition the read-write pointer within a file, check attributes, and truncate files, cut them short. All the basic management operations.
Yeah, and organizing them. Directories.
Yes. Simple systems might have just one directory, but realistically you need hierarchical structures. Tree-structured directories are common, like folders within folders. Some systems allow more complex acyclic graphs using links or shortcuts.
But allowing cycles, like a link pointing back to a parent directory, causes problems.
It can. A general graph structure that allows cycles makes it really hard to know when it's safe to delete a file or directory. You might have circular references, keeping things alive indefinitely. It creates a garbage collection problem figuring out what's truly unused. Most file systems avoid general graphs for this reason.
Pintos makes students build some of this. Subdirectories, paths.
Yeah, the file system project is a big step up. You implement dynamically growing files, extensible files, subdirectories, and handling both absolute paths, like a usurban, and relative paths, .images.
And it even gets into details like doubly indirect blocks.
Right. To handle potentially large files efficiently on a limited disk partition, Pintos uses a technique where a file's control block doesn't just point directly to data blocks. It might point to an indirect block, which is full of pointers to data blocks. And for even larger files, it might point to a doubly indirect block, which points to other indirect blocks, which then point to data blocks.
Like an extra layer of indexing.
Exactly. It allows the file system to manage large files without needing huge, contiguous chunks of disk space initially. It's a practical data structure choice driven by real-world constraints.
Okay, let's connect outward. Distributed systems and networks. What are the big advantages?
Well, the obvious one is resource sharing files, printers, specialized hardware. You also get potential computation speed up by distributing tasks across machines, load sharing, or job migration. Reliability can improve because if one machine fails, others might take over. And of course, communication between users or processes.
And distributed file systems, DFS, are a key part, like NFS.
Yes, NFS, Network File System, is a classic example. It allows you to mount a directory from a remote server so it appears as part of your local file system. Makes accessing remote files much more seamless.
But naming things in a network gets tricky. Location transparency and independence.
Those are important goals. Location transparency means the name of a file doesn't tell you where it's stored physically. Location independence means the name doesn't have to change even if the file moves to a different server. Both make the system much easier to use and manage, hiding the underlying network complexity.
All right, let's look under the OS's own hood. Protection and security. Why the distinction?
Protection is about mechanisms within the OS to control access to resources, ensuring process A can't corrupt process B's memory, for example. It ensures orderly operation. Security builds on protection, but also deals with external threats, preventing unauthorized access, defending against attacks, ensuring data integrity and confidentiality.
And techniques like role-based access control, RBAC, help with that.
Definitely. Systems like Solaris use RBAC. Instead of assigning permissions directly to users, you assign permissions to roles, like database admin or web server manager, and then assign users to those roles. It often enforces the principle of least privilege. Give users and programs only the exact permissions they need to do their job, nothing more.
Encryption is obviously huge, too.
Fundamental. For confidentiality, ensuring data can only be read by authorized parties. You have symmetric encryption, same key to encrypt, decrypt, and asymmetric public-private key pair used for different purposes like secure communication or digital signatures.
The threats are always evolving. Buffer overflows, denial of service.
Constantly. Buffer overflows are classic programming errors where writing too much data into a buffer can overwrite adjacent memory, potentially allowing an attacker to inject malicious code. Denial of service attacks aim to make a system unavailable to legitimate users, maybe by flooding it with traffic. OS security is an ongoing battle.
Even mainstream OS like Windows 7 had sophisticated features for this.
Oh yes, things like access tokens to represent a user's identity and privileges, detailed access control lists, ACLs, on objects specifying who can do what, and even integrity labels to prevent less trusted programs from modifying highly trusted files. It's complex machinery.
Now, the huge innovation, virtual machines and hypervisors. How do they fit in?
Hypervisors are software or firmware that create and run virtual machines, VMs. A VM is like a complete simulated computer running its own operating system, the guest OS, on top of the physical hardware managed by the hypervisor.
And Type 1 hypervisors run directly on the hardware.
Yes, they are often called bare metal hypervisors. They essentially act as the primary OS for the hardware, whose main job is to partition the resources and manage the guest operating systems. They're the foundation of modern cloud computing and data centers.
The most mind-blowing feature has to be live migration.
Isn't it incredible? The ability to move an entire running virtual machine guest OS, applications, everything from one physical server to another, across the network with practically zero downtime. Users often don't even notice it happened. It's a game changer for maintenance, load balancing, and disaster recovery, far beyond what a traditional single OS could do.
Finally, we have to touch on the open source movement, Linux, GNU.
Hugely important. Linux is the prime example of a successful open source OS kernel. But the philosophy goes back further to Richard Stallman's GNU project and the Free Software Foundation, championing the idea that users should have the freedom to run, copy, distribute, study, change, and improve software.
And the copyleft idea with the GPL license.
Right. The GNU General Public License ensures that if you modify and distribute GPL licensed software, your modifications must also be available under the GPL. It encourages sharing and prevents proprietary lock-in of derivatives.
And this openness is great for learning, isn't it?
Absolutely. Being able to actually see the source code, modify it, compile it, and run your changes, that's an incredibly powerful way to understand how something as complex as an operating system really works. It's the philosophy behind educational projects like Pintos.
Wow. We've covered a lot of ground, from the absolute basics of hardware management and processes, right through virtual memory complexities, file systems, networking, security, and even into virtualization and open source. Seeing how the textbook theories play out in practice with something like Pintos is really illuminating.
It really is, and it makes you appreciate just how much invisible work is happening every time you use any digital device. These layers of logic, managing resources, providing abstractions, it's quite an achievement.
It definitely makes you think all this complexity is hidden from us now. What new layers of abstraction, what new functionalities are being built right now that will shape the next generation of computing? And what completely unexpected challenges will those innovations bring for the operating systems of tomorrow?